Hello everyone, this is Mrigank from Purdue. I'm going to present my work on energy efficient MRAM access scheme using spin torque based current sensors. This is a brief outline of my talk. First I will describe the motivation behind this talk, why we are looking at MRAM as a memory technology, and then why we are planning to explore spin torque sensors for access schemes, and why at all we are considering low power access scheme for MRAM. How does it matter, and how big a problem it is going to be in future. Then I will describe the spin torque based current sensor, one of the basic devices that we have proposed, and how it can help us achieve very low power memory operations for MRAM. Let's get started with the first slide. So here, the first picture shown over here is the conventional SRAM cell. And it is well known that as the CMOS technology scales down, the basic problem of this standard SRAM cell is large leakage and other robustness issues emerging from variabilities problem. So if you look at the pie chart over here, which shows the total energy components of the SRAM, at 32 nanometer node, the leakage energy is going to be the dominant in SRAM technology. Apart from energy consumption, there are of course other challenges which the SRAM technology faces. And most of those are related with variability issues at scale technology nodes. In last decade, several post-CMOS technologies have been explored as a drop-in replacement for SRAM. And one of the most widely accepted drop-in replacement for SRAM has been identified as MRAM technology, or STT-MRAM technology. STT-MRAM stands for Spin Transfer Torque Magnetic RAM. It is a non-volatile memory technology which stores information in the form of spin polarity of magnets. So the MRAM cell constitutes of a magnetic device as shown over here. It has two magnets showing blue color separated by a tunneling oxide over here. So for spin polarity of one of these magnets is fixed to one direction, whereas the other can be flipped either parallel or anti-parallel to the other magnet by injecting charge current across this device in either direction. When both the layers are parallel, the resistance of this device is smaller, whereas when these two are anti-parallel, the resistance is higher. And the ratio between these two resistances can be a factor of 2 to 3, and the absolute value can be in the order of kilo ohm. In order to sense this resistance of this device, we can use a constant charge injection, and hence we can sense the voltage developed across this device by comparing it to a reference voltage, and hence we can distinguish the two levels. So one of the most important advantages of STT-MRAM is that it is a non-volatile memory technology, and as a result the leakage energy is very small. And apart from that, density comes as another big advantage. Here each cell uses just one transistor as compared to 6 in an SRAM. One of the disadvantages of conventional STT-MRAM is write energy. In order to write in the free layer of this cell, we need to inject a good amount of charge current across a large voltage, and that constitutes a good amount of write energy per bit cell. But in last 5 years, the solution to this problem have been explored widely, and several low energy write schemes have been proposed and demonstrated experimentally. One of them is a domain ball based write, in which there is a separate terminal for writing, and it does not inject charge current across the tunneling junction, but it uses a separate terminal for low voltage write. So such schemes can reduce the write power, and as a result, with a relatively small voltage and small current, we can reduce the write energy by a factor of 10 or more as compared to the conventional MRAM. So now, if we look at the most probable scenario for MRAM, this is going to be the energy division for the MRAM technology. Most of the energy is going to be dissipated in read and sensing operations, which also includes the data transport. Here, the energy dissipation for two-level cache with MRAM has been shown. It shows that two most predominant energy components are the one due to charging and discharging of the metal bit lines for sensing operation, and the other is for data access through the H3 data bus. So if you look at the general cache architecture, it has a H tree-shaped data bus, which is used to access the individual memory array. And in each of these memory arrays, we have bit lines which are used to charge and discharge based charge reading operation. So since these are the global metal lines, their charging and discharging constitutes most of the power consumption in such a non-volatile memory. So this is the main reason why we are exploring alternate schemes for low power reading and memory access. So in the rest of the talk, I will try to explain why emerging spin torque sensors proposed as a part of this work can give us very low power solution to these two operations in memory, namely the sensing and data transport across data buses. Now, if you look at the conventional MRAM sensing scheme, the two most common methods are voltage mode or current mode. In the first scheme, current mode scheme, we can inject a constant current across this resistive memory cell, and the voltage developed across this can be sensed using a voltage sense amplifier. And a complementary method is to apply a constant voltage and sense the current generated through the resistive memory using another current sense amplifier. Both these methods use sense amplifiers, which are analog circuits, and they are significantly complex in terms of area, as well as they consume quite a good amount of power. Each of these sense amplifiers can be pretty large as compared to each of the memory cells, and as a result, we cannot afford to have dedicated sense amplifiers for each of the memory columns. Effectively, a large number of memory columns, as shown over here, they need to share a common sense amplifier, and as a result, they need other peripheral circuits like analog multiplexers formed by transmission gates. As a result, these kind of analog sensing schemes turn out to be power hungry as well as slow, and the energy dissipation can be found out by looking at the two major components: the static power because of the read operation itself, and the power consumption in the sense amplifier. And it turns out to be few tens of femtojoule for each bit. Now, the second energy component, as I described earlier, was the data transport scheme. So, since most of the power consumption in a memory array comes from the H-tree data transport, people have explored methods to lower the power consumption in the data buses. One of the methods is to use low swing current mode data buses, in which rather than charging the data buses to full voltage scales, we use static current injection across these metal lines. So, for example, here we have a current mode transmitter which injects some amount of charge current across this transmission line. At the receiving end, we have a transimpedance amplifier which receives this current and converts it into full swing voltage. In this scheme, although the CV square power dissipation on the metal line can be almost eliminated because it's a current mode transmission scheme, but at the receiving end, we need an analog mode transimpedance amplifier, which again consumes a good amount of power as well as area. An optimized design in 45 nanometer CMOS technology happens to consume around it gives us around 3x power benefit as compared to conventional method. So although we are incurring a good amount of hardware complexity by introducing these analog mode transceivers on on-chip data links, we do not get a huge amount of benefit. It remains around 2 to 3x as compared to conventional voltage mode links. So we'll see how spin torque based sensors can help us achieve very low power for these current mode data buses as well as current mode sensing schemes. So one of the possible current mode sensing devices shown over here is based on spin torque switch. Here, this spin torque device has two fixed domains, upspin and downspin, having domain 1 and domain 2, and there is a free domain. There is a free domain, domain 3. Depending upon which of these two domains, domain 1 and domain 2, receives larger current, the spin polarity of the free domain can be flipped parallel to either domain 1 or domain 2. So effectively, this device can act as a current comparator and senses the difference between two inputs. And the free domain is effectively a low resistance metallic channel which can be biased at a very small voltage. So we get current mode comparison at a very small voltage, and simultaneously these devices can achieve a high switching speed. And recent experiments have shown that sub-nanosecond switching is possible if we are able to scale these devices down. Device operation, micromagnetic simulation for device operation is shown over here. It shows comparison operation for two current levels, 10 microampere and 5 microampere through two branches. And we see finally the free domain, the leg of the T, is finally switched parallel to one of the input domains because the current through one of the domains is larger. Note that, as we said earlier, since the right current path here is a metallic path, the input voltages applied over here can be very small. It can be few tenths of millivolts. As a result, we can get very low power sensing operations. So how do we apply this sensing device for accessing the MRAM? First is the read scheme. So in this case, we connect the bit line of the MRAM to the sense amplifier and apply a very small read voltage, which can be 50 millivolt. The resulting current can be sensed by this sensor. One of the input is connected to the MRAM cell, while the other is connected to a reference input, and the spin polarity of the field layer depends upon whether the MRAM cell is parallel or anti-parallel state. So we get very low power operation for read because we are first of all we are using very small read voltage for read operation. At the same time, the circuit over here decouples the read operation for the spin torque with the digital data conversion. So here we are using a minimum size CMOS latch to convert the spin mode data stored in the sense amplifier to a digital data. So this is essentially a two-stage comparison. First stage converts the MRAM data into the spin mode information in the sensor, and second stage, a minimum size latch, converts the spin mode information back to a digital data. So because of low voltage and fast read provided by the spin torque sensor, we can get an order of magnitude reduction in read energy as compared to the conventional analog read schemes. Now let us look at how we can use the same device for very low power data buses. So here we show a current mode interconnect based on the proposed spin torque sensor. One of the input is connected to a reference current, which is again flowing through a very small voltage, and the other input is receiving the current mode data received across the copper interconnect. So here we have a long data bus, which can be of the order of 10 millimeter long, and it is receiving a current mode data input from a driver across a very small terminal voltage. So since the right path of these devices is a very low resistance metallic path, once again we can bias the whole interconnect link at a very small terminal voltage of the order of few tenths of millivolt, and as a result, although we are using current mode data transmission, the static power consumption because of the current mode data transmission is very much reduced. At the same time, the magnetic tunnel junction formed with the free layer can be used to detect the spin state of the free layer without incurring any additional power consumption. So the magnetic tunnel junction, since it acts as a resistive device and its resistance depends upon the relative polarity of the two layers, so a magnetic tunnel junction formed at the top of the free layer compares the spin state and converts it into a digital data. So if we compare the power consumption of the proposed spin torque sensor with conventional current mode data buses, we can once again get close to 2 orders of magnitude reduction in power consumption. So we see that this spin torque based device can be used to build very low power current mode data buses as well as very low power sense amplifiers, which are used to access the MRAM. So the two major power components in the MRAM technology, namely the sensing power and the data bus power, can be drastically reduced by application of these emerging current mode sensors. Finally, this is a simulation framework we have used in this work. So just for a note, most of the device structures fabricated in this field are at this stage at large scale. In this model, we have assumed that these devices can be scaled down considerably, and we have done thorough device level analysis and simulation modeling based on device physics, and we have extracted SPICE simulation models from those device physics based models and used them in circuit architecture level simulations. So in conclusion, we identified that emerging spin torque switches can be very suitable for current mode data communication and sensing schemes, and spin torque based sensors can give us very low power memory access schemes, which are going to be the dominant, which are going to contribute significantly to the power consumption in future memories. So of course, there are many challenges, like scaling down of these spin torque devices is a big challenge, and we are exploring methods which can give us high speed without drastic scaling of these devices. And along with that, we will explore the effect of circuit and architecture level optimization in the proposed scheme. Thank you. If you have any questions.